Hello everyone. Today we are going to understand PostgreSQL architecture, the database architecture. See, if you look at the database architecture of PostgreSQL, you will find two things. One is the instance, the Postgre instance, which is residing in your RAM or your memory, and the other one is the persistent storage layer. This persistent storage layer is nothing but where your actual data is residing, and this instance is nothing but where your background processes, your buffer memory, they all reside. And it's a client server model where client is connecting to the instance and instance is then connecting to the persistent storage. So let's understand how this process works. So there could be multiple client applications. It could be like a PSQL, any other client applications like Java, .NET, Python, and could be PG admin. So these kind of client applications, they will connect to the PostgreSQL instance using the TCP IP. So what they will do is first it will connect to the Postmaster. So this Postmaster, it is the master process of the PostgreSQL instance. You could say it's a listener. So what it does is basically it will authenticate, it will check all the things, and then if the authentication and everything is fine, it will create a background process for that client. That's it. I mean, here client won't be interacting with the Postmaster. Now client is directly connected to the background process. So that's the first step after the authentication is done. Now each and every background process that is connected to the client. So if there are 100 clients which are connected, then we'll have 100 background process. Now each background process has a local memory. So every process, background process, will have its own local memory to do its own stuff. Say like we have three different types of memories inside our background process. First is work memory. Say your SQL needs to do sorting, hash join, merge join, etc. So it will use your work memory. Say if you are creating a temporary table or all those stuff, then it resides in the temp buffer. And for your maintenance work activity, like there are octo vacuum, creating index, etc. So this is the memory which is being utilized. Then we have the shared memory. When we say shared memory, it is being used by all the background process. Now this shared memory has two buffers. One is shared buffer and the other one is a write ahead log buffer, which is called as WAL buffer. So just keep this in mind. Every background process has a separate local memory, and all the background process use this shared memory called as shared buffer and write ahead log buffer. Now, what is the significance of these buffers? Shared buffers. So when you execute any query, say like select star from employee, what happens actually? Your data resides in the data files, that is in a persistent storage layer. So every time when you execute the query, it is not going to hit your physical disk. So what it will do is first time when there is no data in the shared buffer, it will go and fetch it from data files and put it in the shared buffer. Say other background process also executes the same query. Now this time it will not go to the physical disk, it will get it from the shared buffers. So that's the advantage that we get with the shared buffers. We are reducing the IO contention on the physical disk. Now these shared buffers basically have dirty data as well. When we say dirty data, say I run a update statement. update bank account, sorry, amount equals to 5,000 for a particular customer. Now that particular updated data resides in the shared buffer. When we say dirty data, it means it is not committed yet. So once it is committed, it is pushed to WAL buffer. Now WAL buffer will actually keep on continuously pushing the data to the WAL storage. Now you would say why WAL is doing this? Why after commit shared buffer is not directly pushing it into the data files? So if you understand the flow, say client sends the update, it updates the shared buffer. Now it also creates a recording WAL buffer. Now you have requested a commit. So when we request a commit, shared buffer doesn't directly flush all the data in data files. Say imagine once you commit, say this WAL is not present. So you commit and we return the success, right? Then what will happen? Say there is an instance failure. You would we would lose actually all this data in the buffers because it's in RAM, right? The instance is gone. It is still not returned to data files. But what you got is commit is successful. So here we are compromising with the transaction status actually. There is no durability and recovery. So to add durability and recovery, we use the WAL buffer. Plus, say if I say that okay, I will push all the data from shared buffer to data files. Now there are thousands of commits which are happening at a time. If we do that, there will be huge IO contention that will happen, and obviously you will see slowness in your transactions. So to avoid that, what Postgres does is it's basically once they commit the transaction, there is one entry which is being flushed to WAL storage. Now, once this is done, you are returned, it is successful. The transaction is successful. Say now at this stage, your instance goes down. And once you bring up this instance, this WAL storage data is being used to actually recover. So you get the correct status of the transaction. And your data is also in correct state. So that's the advantage of this WAL buffer. This is nothing but write ahead log buffer. Now, what this write ahead log buffer, how does it write actually to WAL storage? It uses WAL writer. If you look here, there is something called as WAL writer. Now there is also a background writer. Now what this background writer does is it continuously flushes data from the shared buffers so that there is enough memory in the shared buffers, right? So all the dirty data is being flushed into the data file by the background writer. Now you would say my transaction wasn't committed, but still it is being flushed. So Postgres mention actually maintain some version you could say which is called as MVCC, multi-version concurrency control, through which it identifies which is the committed data and which is uncommitted data, and it can ignore that or that particular data is invisible. So that's the idea. And what background writer does is continuously flushes the data from shared buffers. And what auto vacuum does is, see these all uncommitted data, right? Once data is committed, it's a dead data. So all this dead data is being removed by this auto vacuum. So that is what is mentioned in dead tuples. So dead tuple is created by this background writer. And what is the checkpoint process? Checkpoint process basically whatever dirty data is present, which is committed actually, is pushed to the data file. That's the checkpoint. And this runs actually maybe in lesser frequency compared to background writer or WAL writer. And then there are other processes like archiver, So if there are archiver, then it goes into the archive file, and there is a logger process, and then the process monitor basically keeps on monitoring the processes. If the processes have failed, it will restart the process. And we have other files, important files like commit logs, control file. You could say the memory or the heart of your instance, statistics files, so all those stuff. And then there is also a replication launcher. So if there is a replication process, so these are the important background process here. WAL writer, which you already discussed. So it will use the WAL writer and put it in the WAL files. Background writer continuously pushes into data files. It doesn't care whether the transaction is committed or not. Check pointer, it will basically keep when it runs the checkpoints. So checkpoints is basically creates a recovery point, and it stores it into the data field. So once this is done, let's understand how the query is processed inside the PostgreSQL instance. Say I send a query like select star from employee. What happens actually inside? The when we execute this query, it is first parsed, that is syntax and semantics validation, everything happens at this level. And then suppose if I'm using some view, or there could be some rewriting which Postgre will do internally, which you don't have to worry about. So this is a rewriter process, and then starts the planning. Basically, what Postgre will do is it will generate multiple plans, and it will see which is the best plan to execute the query. And once it gets the execute plan, then the executor will execute the plan. And then plan will have different types of access methods, like it could be index scan or bitmap scan or etc. Like table scan, all those stuff. And then there is a storage manager, which is a buffer manager, which is interacting to your shared memory. So this is the high level details of the PostgreSQL architecture. So just to recap, the client connects to your PostgreSQL instance. There is a master process, which is a listener. It will create one background process. Now client is connected to the background process. Background process has its own local memory, and all the background process also share one common memory, which is the shared buffer, then the WAL buffer, and then every query is being processed using this flow, that is parser, rewriter, planner, executor, and there are various background processes which interact with the buffers and the physical disk and make sure that uh, database is in right state and it follows all the asset properties. And as far as the physical storage is concerned, data file is your main database file, while storage is your write ahead log for durability and recovery, and archive is for archive WAL files. And then we have the other parameter files and log files, etc. And just to reiterate the process, say client sends the update, it modifies the shared buffers, it creates a WAL record, then it requests commit, WAL flushes to WAL files. Success is written to client. Once they return to WAL files, now Postgre is sure that it can recover the instance. And then later, there is a background writer check pointer which writes the dirty data to your data files. So thank you so much.